Here we have a circuit with a supply system of 20 volts, a resistance of 100 ohm, and a capacitor of 0.10 farad. The resistor and capacitor are connected in serial and to the supply system. We also have a switch or circuit breaker out here so that we can short the capacitor and discharge the capacitor. So right now the current will flow through the resistor and the switch and back to the supply system. And we can see that we have 20 volt and 100 ohm. It will give us 0.20 amp, and we can measure it here. We can also measure it up here, because here we measure the current and over time. So on the x-axis we got the time, and the y-axis is the current. The current is here negative because with this clamp on we cannot decide if it has to move one way or the other. We also measure the voltage across the capacitor with a voltmeter, and also with this instrument, it is called oscilloscope, and here instead of the current we measure the voltage, and again over time. So if we open the switch and try to do that, we can see we got a charge on the capacitor, positive and negative, and the current will flow through the capacitor and not through the switch. We can see it build up the voltage, but it is not linear, and we'll try to find out why that's not linear. And it is because at the beginning there is no charge on the capacitor because it is shorted. So we can see over here the charge. If the charge is 0, the voltage must also be 0. But when you open the switch, we can see that then the charge will increase because we have a current over time. So we can actually calculate the charge, and we can see if the charge increase, we can see the voltage across the capacitor will also increase, and it depends on the capacitance of the capacitor. But we have to realize that if the voltage across the capacitor increase, we will not have 20 volts over the resistor, and if we don't have 20 volts over the resistor, the current will not be 0.2 amp. We can see already now it seems to be that the current is nearby 0 amp. So just when we open the switch, the current will decrease, and we cannot use this formula because this formula is only when we got a constant current. So we have to use another formula, and it is down here. Here we got, as you can see up here, we use U instead of V for the voltage, but I think you can handle it. So the voltage across the capacitor is equal to the supply voltage multiplied by 1 minus an Euler's number, power 2, minus the time divided by R, the resistance in ohm, multiplied by the capacitance in farad. We use a lowercase letter u out here because it is an instantaneous value, because the value will change over time. So it's not a constant value. So we just want to calculate the value for the voltage over the capacitor in a given time, in a short moment. And here we can try to find out, for example, the voltage across the capacitor if we got 10 seconds and a resistance of 100 ohm. We just put in the numbers and can use the calculator to find out. So 20, enter, 1, enter, and then we have to calculate this fraction, 10 plus minus, enter, 100, divide, 0.1, divide, and we have key on the calculator e power to x. We use this one to find out this value. So left shift key and Q, we got ex. So this number is 0.367. We subtract that from 1 and multiply by the supply voltage. So we got 12.64. So now we can try to control it. If we close the switch, we discharge the capacitor. You can see it gives a flash. So actually you shouldn't do that because there's much energy in the capacitor, and when you short it, you take out the energy in a short moment. So normally we will have a resistor in serial up here, but here at test it is okay. So now we'll open the switch, monitor the time, and see when the time of 10 seconds if we got the voltage of 12.64. So I'll open the switch and tell you the time. Two and a half seconds, 5 seconds, 7.5 seconds, 10 seconds. Yes, it seems to be okay. And we can see that the voltage will increase, not linear, and the current will decrease. And we can see here the current will decrease. And the voltage up here will go for 20 volts, the supply voltage. Here we can reach 20 volts, but in real life theoretically it'll take a very long time. Now we want to change the resistance for 50 ohm instead. So instead of 100 ohm, we have 50 ohm. Then the current will be double, so it should be 0.4 amp in the beginning. So we just short the switch and change the resistance to 50. And we can see, yes, the current is a double, 0.4 amp. And now we want to calculate the voltage after 10 seconds then, if we got a resistance of 50 ohm. Still 20 and 1, negative 10 for the time, but now we divide by 50 and 0.1, and the x, subtract and multiply, and we got a voltage of 17.29. We can try to control that. Two and a half, 5, we can see the curve is much faster. 7.5 and 10. Yes, it seems to be right. So now the voltage will increase much faster because we have 50 ohm instead of 100 ohm. And we got Greek letter tau. It is time constant for this circuit, and the value are the resistance multiplied by the capacitance. So R multiplied by C, 50 multiplied by 0.1 in this situation, so we got 5 seconds. So in this circuit we have time constant of 5 seconds. We can try to adjust the time up here for 5 seconds and try to find out the number if we got 5 seconds. So now we have the time up here as the same as the time constant, and the time constant is down here because it is R multiplied by C. So this fraction should give -1. So 21 answer. We can try to find out 5 plus minus, divide by 50 and divide by 0.1. Yes, the fraction gives -1. And this number we subtract from 1 and we got 0.632. So all times when we have a time constant of 1, we have a voltage which reaches 63.2% of the supply voltage. So for one constant, time constant, always 63.2% of the supply voltage. And it gives us 12.64. Oh, that's the same number as up here. But we can see that up here that we got a time constant of 10, and here we also have time of 10 seconds. Normally we say that the capacitor will be fully charged when we have 5 time constant. So 5 times 5 seconds, it must be give 25 seconds. It is not completely charged, but it is nearby the supply voltage. We can try to find out the value. And we have 5 time constant, so this number must be 5, -5. And now we can see we have a charge of 99.33%, and that's nearby fully charged. It gives 19.87. So 19.87 after 25 seconds. We can try to find out. Two and a half, 5, 7.5, 10, 12.5, 15, 17.5, 20, 22.5, and finally 25. Yeah, I think it was 19.88. So yes, fantastic, and we are very, very near the supply voltage. So that was a circuit of an RC circuit, we call it, where we got a resistor connected in a series with a capacitor, and we can calculate the voltage across the capacitor at any time. And we also find out that this formula up here, we cannot use it in this iteration because the current is not constant.